Suppose that we have a principal ideal domain and T and overring. Let me remind you. Means T is some ring between R and its quotient field. I like to sometimes for domains, I like to think of the quotient field as still the biggest localization you make, right? Because you turn everything possible, that is everything's at zero into a potential denominator. Then T are localized S for some S in R. So if you have an overring of principal ideal domain, then there is some magical subset that you can find if you stare long enough, such that T is R localized to S, right? This is actually kind of a rare property. And I'm not going to show you how this works. This is a homework problem, and it's kind of a fun one. Also, a PID is a UFD of dimension less than or equal to 1. This is also in the homework next time. And what do I mean by this? So classically, probably all of you have seen at some point in the past that PID applies to UFD. And I know I always wonder why, okay, what does it take besides UFD to get you a PID? It has to be a small UFD. That is, the dimension is less than or 1, equal to 1. That means that either prime ideals are maximal, but in the case of the domain, zero is always a prime ideal. So if zero is a maximal ideal, it's a field. So dimension 0 means field, and that's silly. Or it means that any non-zero prime ideal is maximal. Like in the ordinary integers, you've got the 0 ideal, and then you've got these maximal ideals that are generated by primes, 2, 3, 5, and 6, right? This is from the homework too, and the reason I bring this up is this is actually a two-dimensional UFD. I'll state this. I'll prove to you that the dimension's at least 2. It's easy to verify that these 3 are prime ideals, so I can stack it at least 0 and 2 high. The fact that that is as high as it goes might be a little bit less than clear at this point, but you can hear me now and believe me later. But even for this two-dimensional UFD, this no longer holds. There are overrings of this that cannot be realized as localizations. And that's kind of the last thing that I left you with is an example like that last time.
Question,
Yes.
is this for a prime ideal or just any multiplicative set?
No, it's not necessarily the complement or prime ideal. It's you've got to sniff around and find out what this set is, right?
It's no structure that we're assuming other than multiplicative.
That's right, multiplicative closed set. Actually, you can also assume it's saturated if you like, because here's something that you might think about doing. Or is main. Well, more generally than this, but then R localized at S is R localized at S bar, where F bar is the set of X in R such that X is X divides S for some S. This is what I like to call the saturation of R. And here's the reason. Let me give you kind of a sloppy way if you want to play around with this and find out why this is true. If you have A, B, and S, and R is in R, Well, then what this means is AB is a denominator, right? And so R over AB is in RS, right? But if you multiply this times A over one, it's still in RS, right? And this means that R over B, well, actually, let me just take this out of the equation because needlessly kind of confusing things. If AB is in S, then one over AB is in RS. And so one over B is in RS. So notice how you pick up the divisors here. Right, so localizing at a set is the same as localizing at its saturation. Okay. So theorem 1/4. Let R be a commutative ring with identity, and that's multiplicably closed subset of R. Um,
Excuse me,
yeah.
in this one, so you assume that one is in S.
No, I'm assuming one is in R. Because I'm taking one to be my numerator. I'm certainly assuming here in this little blurb that R has an identity. And so if you look at R localized at S,
Okay.
then you can certainly have one over something S.
Yeah, but, okay.
Does that make sense?
And in this case, the, like, equivalence relation, you just have the product difference thing is zero, you don't need a zero divisor, because everything is zero.
Yeah, so I was sloppy here and I said it's a domain, but see if you can show that this persists anyway. Yeah, but you're right, you have to worry about the equivalent relation, in more general sense. Yeah, it do mean. Let's do myself So suppose that R is a commutative ring with identity, and S is some multiplicative closed subset of R, and suppose that zero is not an S, then there's a one-to-one correspondence between the prime ideals of R that exclude S. There exists a one-to-one correspondence between prime ideals of R excluding S. And what I mean by a prime ideal excluding S is its intersection with S is empty. And prime ideals or primes are localized S, given by the following correspondence. Let's say primes of R including S, primes of R localized S. P goes to P localized S. And my notation, I think, is suggested. These are ordered pairs or equivalence classes, if you will. Um, So I guess probably, let me think about this for just a heartbeat. Right, I guess this probably works if you have zero in the set two in a very silly fashion, depending on how you define things. Because if S contains zero, then this is empty, right? Because there are no primes that exclude S, because every prime ideal will contain zero and therefore overlap any overlap or multiple, with close set S. In that case, R localized at S will be the zero ring. So you might argue that the zero ring has no prime ideal. So again, it depends on how you make the definition. I'm gonna leave this one as an exercise. I am going to briefly introduce a concept. We're gonna talk about, these bad boys later, but for now, I just wanna tell you kind of what they mean, because they come up in a natural, kind of context. Actually, let me give you let's go from theorem to, example. So I'm gonna introduce this via theorem. Here we are talking about an integral domain. Let B be an integral domain. The following conditions are equivalent. One. For all A, B. You can throw in zero if you want technically, but for all pairs of non-zero elements, B, either A divides B or B divides A. Two, for all omega, well, non-zero, A, or fulfilled B. Either omega or omega inverse is B. Three, B is quasi-local. This means B has a unique maximal ideal. And every finitely generated ideal of B is principal. Okay, I'm not gonna look at this is an exercise. I can show this. Let me make a couple of remarks here. A quasi-local ring has a unique maximum. Yeah, this gets worse before it gets better. A semi-quasi-local ring. Yeah, this almost sounds like music, right? Give me semi-quaver, right? A semi-quasi-local ring has only finite dimension. maximal ideals. So removing the quasi, in most places in the literature, removing the quasi means you're also assuming the theorem. So a local ring is a Noetherian quasi-local. This is one place where I really don't think they thought terminology out before they just did it. We've all been guilty of that. A semi-local ring is a Noetherian semi-quasi-local. Also, a Bezout, right, it's got some fancy accents on it. Bezout domain is, a domain in which every finitely generated ideal is principal. And a Noetherian Bezout domain is a PID. That is correct. So this is the non-Noetherian analog of that. Anybody know an example of a Bezout domain that's not a PID?
You're supposed to ring of entire functions.
That actually, that does work. The ring of entire functions, for example, the ring of all algebraic integers also has this property. Actually, any valuation domain of dimension bigger than one has this property, as a matter of fact. We'll look at some examples of this in a moment. Let's prove the theorem. Okay, since it's so easy to do and I might want it, I'm just gonna show the equivalence of 1 and 2 first. Fine. This is essentially the definition. So suppose we have 1, let omega, well, so suppose you have a non-zero element of quotient field, then omega is A over B for some A and A, or AB and B. Therefore, since A divides B or B divides A, omega or omega inverse is infinity. Because if B divides A, then it's already there, and if not, then A divides B and its inverse is in there, right? Easy enough. 2 implies 1. Suppose A, B are in B, but not 0, then A over B is in K and is not 0. Since A over B or B over A is in B, then A by B or B by A. Easy, right? This is the more interesting part. So I will now consider 1 and 2 as just a solid brick that I can, club this theorem over whenever I want. Okay, so let's suppose that we have properties 1, 2. We need to show that B is quasi-local, so we need to show that B has unique maximum. Any ideas on how we do that?
Show the ideals are linearly ordered.
Right, in general, ideals are linearly ordered, so let's do that more general statement, I like that. I claim first that if I and J are any two ideals. See how the process of proving things sometimes gives you even more good stuff than you bargained for. Ideals, then one of these two has to happen, right? Wow, that's pretty restrictive, right? I mean, just think about the ordinary integers, right? Most ideas are completely not comparable at all, but, all right, so why is this true? Well, how about a picture? To start us off. If you've got two ideals that aren't comparable, you've got to have a situation like this, right? I mean, because after all, they do have to overlap some because they both contain the 0 element, right? So let's do this here. If not, then there exists X in I, not J, and Y in J, not I. Correct? One of them has survived. So without loss of generality, because I'm a lazy, lazy man, say X divides Y. Right? So Y is Vx or some dB. Therefore, Y equals Vx, which is of course in I, which is a contradiction. So we've actually shown a much stronger result since all ideals are linearly ordered. There can be at most one maximal ideal. And we know this is a commutative ring with identity, so it has maximal ideal. A unique maximal ideal. So we have a quasi-local domain. Now we have to show that every finitely generated ideal is principal. I won't go through all the blood and guts of this one, but you can do this by induction on the number of generators. You see every finitely generated ideal principal induct on the number of generators. Right. This is clearly true for one generator. So suppose that we can induct this way. Notice that suppose that if I exist, then I is principal. Okay. So suppose the statement, holds for some n, right? Okay, now suppose we've got n+1 generator, right? Which, this is the same thing as, let's call it J X n+1, where J X n, right? So now we have the n+1 case. Well, we know that this is synonymous with Jn, where J is generated by these first n variables. Inductively, this is generated by A. So I is generated by A xn+1. Right? If A divides xn+1, then I is A, and if xn+1 divides A, then I is equal to xn+1. And there you go. Right? Inductively, all the ideals are finite, or all finitely generated ideals are principal. Okay. For the last bit, what if you have a quasi-local Bezier domain? So it's local, well, I'm sorry, it's got a unique maximal ideal, and you know that every finite generated ideal. Fine. So, pick your favorite two non-zero elements. B, I gotta prove one of them divides it. Okay, any ideas? Well, first thing I'm gonna do is, I think this is the ideal approach. I want to consider the ideal generated by A and B. What do I know? It's principal, so it's two generated, which is finite, so it has to be principal. And I will let it, and I'm gonna make a very suggestive notation here. This is principal, it's generated by D. By the way, what do you suppose is true about D? It should be like, it should be a common divisor, and in a certain sense, it should be the greatest. So let me point out that because of this inclusion implies, note, D divides A and D divides B. Has to be, right? So just for convenience, if I need it later, I'll write this. A equals D A prime and B equals D B prime. And there's another important fact that I can glean from that ideal equality. What is that?
D equals AB plus BB.
Right, so D has to be some linear constant, because D has to live here, right? So there exists X and Y in D such that D equals AX plus BY. Now notice, this is equal to, what is it equal to? It is equal to d a prime x plus d, b prime y. So I get the following equation. One equals a prime x, b prime y. How does that help? Or does it?
So the one of A prime and B prime, has to be.
That's exactly right. And how do we?
Well, they, if not, then they live in a unique maximal ideal.
Since B is quasi-local, we have unique maximal ideal M, A prime and B prime cannot both be elements of M. Because if they were, this would be an M and this would be an M, so one would be an M. So everybody okay with that? They can't both be an M because that would force the left-hand side of the equation to be an M, right? So without loss of generality, say A prime is not an M. And what does that mean? Oh, poor thing, you don't live in a maximal ideal. In this case, it means A prime unit in D. There is only one maximum. Right? So if A prime doesn't live in that one maximal ideal, it doesn't live in any maximal ideal. And there's only one kind of element that doesn't live in any maximal ideal, it's called a unit, right? So, how does that help?
The ideal generated by D is just the ideal generated by A, so.
Okay, that's right. So since A, since A prime is a unit, then A and D are associates. Right? Because this equation right here says that A and D just vary by a unit, right? Since B divides D, since D divides B, this implies A divides, B. And so B is a value. Because we've shown that one A, in this particular case, A divides B.
But
Yeah,
you
you question.
find it, so you didn't find the issue.
I'm sorry?
You didn't define it, what is the mission domain?
After all, I forgot to say, here, let me patch that up real quick. Remark, a little late. Any domain satisfied. One. Hence, all. The conditions of theorem 1.5.5 is called a valuation domain. Valuation domain might seem funny terminology, but later in the course, we'll get to why we call it that. But, so what are my conditions for valuation domain, right? Any two elements, one of them divides the other, any non-zero element of the quotient field, either it or its reciprocal has to be in V. Or unique maximal ideal and every finitely generated ideal is principal. Okay. And we even proved the theorem about it. All these conditions are, well, look at us, we're so proud of ourselves. Give me an example of a valuation domain. There is a large class of domains that satisfy this in a very silly way. Fields, right? Now, certainly valuations domains exist. Fields satisfy this. I remember the first time I ever read this, I was like, gosh, these things gotta be real close to fields, don't they? But you know what? I feel like a complete fool spending the last 20 minutes in here proving the conditions of it. Three conditions are equivalent when if it turned out that the only valuation domains are fields, right? Because basically I proved a bunch of stuff that basically can never occur in a non-trivial way. Anybody give an example of a valuation domain that is not a field?
Localize the PID out of prime ideal.
Okay, yeah, that's for sure. That'll work. Let me give something kind of specific. This is actually, so if you want to look specifically at this one, I like this. So all the fractions with odd denominators, right? Can somebody explain why why is this evaluation domain? It's certainly local. What does the maximal ideal look like?
To local or
Well, so if I walked up to you on the street and gave you a fraction, right, with an odd denominator, how could you quickly look at that fraction and tell me if it's in the maximal ideal or not?
It's not a unit, AKA the numerator is even.
If the numerator is even, it's in the maximal ideal. Think of it this way, that's the kind you can't invert, right? On the other hand, if the numerator is odd, you can invert willy-nilly, right? So, and it's easy to see that if you have two of these things, so if you have A over B, C over D, with B and D odd, then you can write A over B as 2 to the K, A prime B, and C over D as 2 to the J, C prime over D. And to see which one divides the other, just compare the powers of two. Whichever has the smaller one divides the other. Right? So this is a large class evaluation domain. Anybody think of another one? Okay, good. A power series ring over a field. And I feel like I'm kind of hanging you guys out to dry on this example because I haven't really talked about power series yet. But if you have some experience in them, the unique maximal ideal is it's just every power series that has a factor of X and 0 if you want to count that way. And everything, and notice that the units are is a set of power series. Since f of 0 is not zero. one of the interesting things about power series that you probably come across earlier is if you have power series, if it's beginning, if its constant term is a unit, then that power series is a unit. And of course, if you're over a field, everything that's not zero is a unit, right? So it turns out that any two power series that are not zero, so if you have two non-zero power series, they look like this. That's the number zero, and F of zero and G of zero are non-zero. So basically, every non-zero element of this ring is a power of X times a unit. So which one divides the other one? Whichever one has the smaller exponent of X. What's true about all the examples, in fact, in a certain sense, these examples look different, but spiritually, they're kind of the same. That's right. Immunoder will love these rings because they are all varied. Can anybody give an example of a valuation domain that is not a theory? Good.
Field with, variables X and Y, and you say, give me Y over X, Y over X squared.
That's right, and you'll have to do some localizations for it, but I mean, you can build valuation domains that are really, really weird. You can build valuation domains where the maximal ideal is the union of all prime ideals strictly contained in it, right? You can build, valuation domains with principal maximal ideal that are infinite dimensional. You can build valuation domains where, given any prime ideal that's non-zero, you can find a smaller non-zero prime in it. Right, so there is no prime ideal strictly containing zero that is minimal over that. So basically you can go down. Actually, those are weird because that one, the complete, if you're interested in computer algebra, the complete integral closure of that one is the entire quotient field. Let me give you a couple of examples. Maybe not quite so exotic. By the way, both of these examples of valuation domains are one-dimensional in the following sense. And in both of these examples, you have zero ideal and the maximal ideal. That's it. Here the maximal ideal is generated by X. Here the maximal ideal is generated by the prime P. Here's an example of a one-dimensional, so you've just got the zero ideal and you've got a maximal ideal valuation domain that's not enough here. So I use this notation. This is sort of a group ring notation. Everybody knows what polynomials are, right? I mean, I'm going to talk about them formally, but you've worked with them. So a polynomial ring, the f, x, the natural numbers. This is the animal where I'm allowed to take my exponents from. So the typical element of this, well, it looks like it's just an ordinary polynomial over a field, except I'm allowing positive rational exponents. So it's just like polynomials that you might have encountered earlier. It's just, I'm generalizing a little bit. I'm allowing my exponents to be rational, positive, right? Or I guess at least zero. Now, let M be the ideal generated by the set X to the alpha. Oops. Alpha strictly whatever you say. So in other words, the maximal ideal is just stuff where the A0 is zero. right? That's it. It's just all polynomials where the constant term is zero. So if you plug in 0 to x, you get this. This is a maximal ideal. And so it's the quickest way to see that this is a maximal ideal. Well, right, but what makes it maximal?
When you mod it out, you're gonna get that.
That's right. When you mod out by this ideal here, you're just gonna get F, right? So it's gotta be a maximal ideal. Let's let V equal R localized at M, which is the set of F of X, using the term loosely, over G of X, where F and G are in R, and G of 0 is not 0. This cuts out all the noise, and basically, so we'll go over some other examples next time, but I think it's do this justice. I am going to sort of computationally show you that this is a valuation domain in the following sense. If I take an arbitrary polynomial from this, so polynomial, let's say a0 x to the q0 plus a1 x q1 plus ak x. Here's what I can assume. I can assume that q0 is at least 0. I will assume all these AIs are not 0, because otherwise why would I have written it down in the first place? So I can arrange these sort of in ascending order, right? So this is at least 0, and my exponents are getting larger. Well, so I can take this animal and I can write this as x q0 times a0 plus a1 x q1 minus q0 plus ak x qk minus q0. Correct? And this thing is a unit in V. So any non-zero element of R can be written in this localization as a power of X, a rational power of X times a unit. Everybody agree with that? And so actually in the entire, because the only thing you're doing here is you're putting more units in the denominator, so that really doesn't matter. So in V, every element is, every non-zero element is a form x to the q times u, where q is greater than or equal to 0, and u is a unit in V. And now, I think it's fairly easy to see that this has to be a valuation domain, because given x to the q, u, and x to the q prime, u prime, one of these has to divide the other, whichever one has the smaller exponent, rational exponent. So this is an example of a valuation domain. And the prime ideals here look like 0 and MV. Notice that this is not Noetherian, because if you have a finite set of generators of this form, just take the smallest one, smallest exponent of your finite set of generators and look at x to the q over 2, and it can't be in there. So the ideal here, in fact, not only that, the maximal ideal here is super yucky because it's idempotent. So when you square the maximal ideal, you get the maximal ideal back. It doesn't get smaller as most ideals are used to. Okay, we'll go over some more examples next time. Any questions?
What is MV?
MV is, you take this maximal ideal here in the first place and then extend it up to V. So it's just the smallest ideal of V that contains all of them. Any others? All right, we'll see you all next time.